Oh, Basil, what's happening, baby?
A lot is happening, Foxy. Dr. Evil has escaped. The good news is that one of our agents has managed to infiltrate Dr. Evil's organization.
Excellent, Basil. We've been trying for years to get a mole inside Dr. Evil's lair, and we now have that mole.
Yes. Ah, and here he is.
So you're the...
Most excellent agent we've ever seen.
Yes, most excellent agent we've ever seen. Thank you.
Thank you. Now, I wasn't able to get an exact location, but I did learn that Dr. Evil has moved to a new lair outside of Tokyo, Japan. By the way, I realized that I have a large mole on my face.
Where? What? Where's that mole? I didn't see one.
I also realized the irony that I am myself a mole.
No one would make that connection.
Anyway, well done, old chap. Jolly good work.
Yes, nice to mole you. Meet you. Nice to meet you, mole. Don't say mole.
Stop.
I said mole.
Stop.
Bye.
Mole. Mole. Mole.
Oh, shut up! Mole, 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 mole.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately, for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, Now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Welcome to what may be the most important word we will use the entire year, the mole. Now, what's interesting about this word mole is that it's a word that means a number. Here's a couple of examples. We know whenever we see the word pear, we know that means 2. We know when we see the word dozen, that equals 12. You might have actually heard of a version called the baker's dozen. And that was when they would try to earn your business by throwing an extra baguette or bun in your basket for your purchase to make it an even 13. You might also have heard of some more obscure ones like score. We hear this in the Gettysburg Address when he says 4 and 7 years ago. That 4 means 4 times 20. Here's another one you might not have heard before. Gross, that's 144, or ream, like a ream of paper, that's 500, and finally a grand, which means 1,000. 1 mole is the same thing, but it's a big number, and here's why. The measuring unit mole is used to quantize very, very, very small items, such as atoms. In other words, when you have atoms that are, or when you have objects that are really small, like atoms or molecules, whose size is on the order of times 10 to the negative 8 centimeters, you need a lot of them to have an amount that's measurable. So 1 mole is 6.02 times 10 to the 23rd. That looks like this. That's a big number, and it's difficult to do on your calculator. So we use scientific notation. So let's bring our calculator up here so we can see what it looks like. Here on your calculator, we have a function here called the EE button. It stands for exponent entry. So on your calculator, when you're trying to enter 6.02 times 10 to the 23rd, it's going to look like this. 6.02. We're going to hit second. See how this little up arrow lights up to show us that we're shifting. EE, and this little E is the calculator's way of saying times 10 to the. And so all we have to do is tell the calculator that we want that exponent to be 23. Now there are going to be some of you that are going to enter it like this. You're going to say 6.02, and you're going to say times 10 to the, you're going to use this little caret function and enter the exponent that way. And that looks great, but I'm telling you that doesn't work. So please don't do it that way. So how do we measure out a mole's worth of atoms? It's actually really simple. So if you look on your periodic table, every element has got these 2 numbers. And we remember that this number here is something called the atomic number, and that is the number of protons. It's also the atom's identity. We're going to ignore that one for now. We're going to focus on this number. If you recall, it's what we call the average atomic mass. And it is the number of protons plus neutrons. And remember that this is an average, and that most examples of carbon are what we call carbon-12, and that means they have got 6 protons and 6 neutrons. What this means for us is that one proton has a mass of 1 atomic mass unit. And so that means that on average, 1 atom of carbon is going to have an atomic mass of 12 atomic mass units, because you've got 6 protons and 6 neutrons. So that's what we're going to call 12 AMU. This value is going to be something else for us. We're going to call this the molar mass. We're usually going to round it. So for carbon, the molar mass is 12. Notice that this is in grams. This means that 12 grams of carbon is 1 mole of carbon. And that means that 1 mole of that carbon, if you have 12 grams, is equal to 6.02 times 10 to the 23rd atoms of carbon. We're going to worry about that later. Let's just crank out a couple of moles and see how this works. Every element has its own atomic mass that is equal to its molar mass. So for neon, its atomic mass is 20.18 atomic mass units. That means that its molar mass is the same value, 20.18 grams. What this means, if you weigh out 20.18 grams of neon, you have 1 mole. And that means that if you have 1 mole, you have exactly 6.02 times 10 to the 23rd atoms of neon. And that's all it is. That means that if you weigh out exactly 15.994 grams of oxygen, you have 1 mole. If you weigh out 31.998 grams of oxygen, you have 2 moles. If you weigh out 7.997 grams of oxygen, you have 1/2 of a mole. So to help us out with this, we're going to use what's called a conversion factor, what you might heard of before as a picket fence. You're all making faces, but a conversion factor is actually a useful tool. What it helps us do is switch from the unit we have to the unit we want. So here's how this works. We're going to start off by identifying what we want. And here is the value that we're starting with. We're going to multiply this by our conversion factor. We're going to put the unit we have on the bottom and the unit we want on the top. When we do this, the unit we have cancels. What we're left is the unit we want. And when we multiply what we have by the unit we want, divided by the unit we have, that spits out our answer. I'll show you what I'm talking about. So here's a question you can expect to see. It's asking, how many moles of carbon do we have if we have 300 grams? So the question is asking, how many moles? are the equivalent of 300 grams. So we have the unit that we want, moles of carbon. We have the unit that we have, 300, and we're starting, the unit that we have, which is grams, and we're starting at 300. So here's how the picket fence works. We're going to set this up with the unit that we have on the bottom, grams of carbon. Unit that we want goes on the top, moles of carbon. And we know from this guy that there are 12.011 grams. Feel free to round. We'll round that to 12 in 1 mole. So that goes right here. In 1 mole, there are 12 grams. Here's our calculator. And we're going to say, let's move this over here so we can see what I'm doing. We're going to multiply across the top, and we're going to divide by the bottom. So we're going to say 300 times 1, which we don't need to do, divided by 12. We're doing this all in one big shot. This is 25 moles of carbon. Okay? See you on the next one. Let me get rid of this. Bye.